Hi students, we are in Avogadro's Law in chapter 7, and this is the relationship between pressure, temperature, volume, and moles. So unfortunately we have another variable to deal with. We've got another letter, and that's moles. And moles is represented by the letter N in lowercase. So first, who did we get this law from? Well, this was named after Amadeo Avogadro, and he lived in the late 1700s and early 1800s, and he was an Italian physicist and mathematician, and Avogadro's number is named after him. And just in case you don't remember what that was, it's 6.022 times 10 to the 23rd. And that's a quantity, and it's the number of things in a mole. So if you have a mole of anything, you've got 6.022 times 10 to the 23rd of those things. So that's a lot of things in a mole. And what Avogadro's law tells us is that if we keep our temperature and our pressure constant, that the volume of a gas in a container that is allowed to expand is proportional to the number of particles present. So that means if we double the number of moles, what we're going to do is also double the volume. So we've got direct proportionality there, and you guys can see that the pressure is being kept constant here, and we also assume that we're keeping a temperature constant because up here it says constant temperature. And what this does for us is it gives us, like I said in the first slide, a new variable to work with. And this new variable is moles, and moles is represented by a lowercase n. So you'll see that appear down here next to temperature. And that looks like a pretty evil equation there because we have 8 variables to work with. But the thing about this is that we're keeping the pressure and the temperature constant. So if the pressure and the temperature are the same on both sides, we can cancel those out. And what we end up with is this little mini version down here that's a little bit easier to remember. So we have V1 over N1 equals V2 over N2. And again, this is proportional. So if one goes up, the other one goes up. And if one goes down, the other one goes down. And in case you're wondering what this looks like graphically, we can move on over here. And we can see that as we increase the number of moles, our volume directly goes up. So we have direct proportionality there and a lovely, nice line there. It's nice and linear there. So that brings us to molar volume of gas. And 1 mole of any gas occupies about 22.4 liters at STP. Now, what is STP? Well, that is our standard temperature and pressure. And our standard temperature and pressure are 273 Kelvin and 1 atm, which is exactly the same as 760 millimeters of mercury, and that's the same as 760 torr. Also, 273 Kelvin is the same as 0 degrees Celsius, and it's the same as what temperature in Fahrenheit? Well, 0 degrees is freezing for water. So what's freezing in Fahrenheit? That's 32. Okay, so this interesting observation about gases, that they occupy the same volume, 22.4, 22.4, and 22.4 at STP, no matter which gas we have, is really interesting because if we look at helium atoms, which we have down here, so we have a mole of helium atoms, our helium atoms are quite small. And if we look over here, we've got methane, and methane is a major component of natural gas. And the methane looks like this. So it is larger than our helium atoms, these methane molecules, except a mole of helium and a mole of methane, if they're both at STP, they're taking up the same volume, which is 22.4 liters. So that's a really interesting characteristic of gases. It doesn't matter which gas it is, if you've got a mole of it at STP, which is 273 Kelvin or 1 atm, or 0 degrees Celsius and 760 millimeters of mercury or torr, you're going to have 22.4 liters of that stuff. So that brings us to some problems. So number 1 says, Jose's balloon contains 1.1 mole of helium, and that occupies 25.0 liters. If Jose lets 10 liters of the helium out of the balloon, how many moles of the gas are left inside? Well, let's go ahead and identify our variables. So if we've got mole right there, that means that variable is going to be a lowercase n. And then if we have 25.0 liters, is that going to be volume, pressure, temperature, moles? Liters is a unit of volume, so we've got a V. Now it says Jose lets 10 liters of the helium out of the balloon. So that means we have 25 minus 10, which leaves us with a volume. So if we have two different volumes, one has to be 1 and the other has to be 2. And V2 is equal to what if he originally had 25 liters and he let 10 out? That will be 15. So V2 is 15 liters. And then right here it says how many moles of gas are left inside. And moles is which letter? Lowercase n. And you guys can see here that we've got two n's, so one must be the first and one must be the second, and we want to make sure that we keep our sets together. So 1 mole of helium goes with 25 liters, and 15 liters is going to go with this n right here. So let's go ahead and list out our variables. So n1 is equal to 1.1 moles, and V1 is 25 liters, and N2, what is that? We don't know that, we're looking for it. And V2 is equal to what? 15 liters. So do we have an equation that relates moles and volume? We do. And that is V1 over N1 equals V2 over N2. And I got that from right here. So we just learned that. And we're solving for N2, so we have to do a little bit of rearrangement here, which means that we have to take N2 and we have to put it in the top because that's what we're solving for. And we have to get it by itself. So we're going to want to move V1 and N1 over to the right-hand side of the equation. So N1 goes up to visit V2, and then V1 is going to come back down to the spot that N2 vacated. So we've got that N2 is equal to V2 N1 over V1. And now we just need to plug and chug. So we have that V2 is 15 liters and N1 is 1.1 mole. And remember, you're going to want to do the 2's and the 1's together, so don't let your brain mess you up there. And then V1 is 25 liters. Now what cancels out? What's the same on the top and the bottom? The liters. So now we have a unit of mole, and that's good because N tells us we're solving for moles. So what we end up with is an answer that has 2 significant digits because 1.1 mole has 2 significant digits, and that's 0.66 moles of helium. And if we look back up at our chart, right here we've got about 0.7, so right in here would be about 0.66 or 0.65. And if we go up here, we can see that we should have about how many liters? About 15 if we've got a little over 0.6 moles. And that's what we have here. We have a little over 0.6 moles and we have about 15 liters. So we're right on with our calculations there. Okay, number 2 says Louise has 37 liters of carbon dioxide at 760 torr and 0 degrees Celsius. What is the mass of this gas? Okay, so right here, 37 liters is what? That's a volume. So we've got a V here, and we have a pressure here, and we have a temperature here. And then it says, what is the mass of the gas? So that's kind of interesting because we've done V, P, T, and N, but we haven't gone to grams. And when we used N, we had an original amount of moles and we were solving for the other one. So those equations that we learned so far don't quite work, but what we might notice about this pressure and temperature is that it's special. That is what? That is STP. So standard temperature and pressure. And where did I get that from? I got it from right here. So we have 0 degrees Celsius and we have 760 torr. And it says if you have 1 mole at STP, you're going to have what volume? You're going to have 22.4 liters. So we can use that relationship and write some conversion factors. So we can have 1 mole of gas per every 22.4 liters, or we can have 22.4 liters for every 1 mole of our gas. Either way, we're going to let our units guide us in this next problem to tell us what we're going to use. Alrighty, so we've got 37 liters of CO2. Now we want to get rid of liters of CO2. And we want to go to moles of CO2 because we know that if we get into moles, we can go directly to mass because we've been practicing that a lot. So we want to put liters on the top or the bottom of this conversion factor here. We want to put it on the bottom because we want to get rid of it, and liters divided by liters is what? Is 1. So we're going to use this version. So we're going to have 22.4 liters for every 1 mole of CO2 because your gas is at STP, so you can use that relationship. So our liters cancel out and we're in moles of CO2, and you guys know how to go from moles to grams. So what we do is we use a molar mass. So we have 1 mole of CO2 on the bottom because we're letting our units guide us and we want the moles of CO2 to cancel out. And then we're going to put what on top? We've got a mass, and what's a unit of mass that we usually use that's in a molar mass? Grams. So we have grams of CO2 up on the top here. Now, how do we figure out what the molar mass of a compound is? We get out our periodic tables and we say, okay, a carbon weighs 12.01. I looked right at the periodic table and I saw that that was the average atomic mass for carbon. So I said 12.01 plus 15.99 plus 15.99, or 15.999 or 16.0, because an oxygen weighs 15.999 or 16.0. So what I do is I add up my two 15.999 plus a 12.01 for the carbon, and I come up with a molar mass for carbon dioxide of 44.01. And I cancel out my moles of carbon dioxide, And I multiply 37 by 44.01. I hit the equal sign, and then I do divided by 22.4. And I take a look at this and I go, okay, I've got 3 sig figs and 3 sig figs and 4 sig figs, and those ones in the 1 mole of CO2 are exact, so they have infinite number of sig figs, so we can ignore those. And our answer will have how many sig figs? It will have 3 because you go with the lower number. So that means that we're going to have 72.6 grams of CO2. Okay, so Joanne has a cylinder of oxygen gas that contains 0.180 moles of O2 at 1 atm and 273 Kelvin. Okay, again, you guys, you've got a special pressure and temperature there, and what is that? That's STP. So again, we know that at STP, if you have 1 mole of a gas, it's going to occupy how much space? 22.4 liters, okay? It says Joanne lets out half the gas. So what's the new volume going to be? Okay, so we've got 0.180 moles of O2, and Joanne lets out half the gas, so we're going to figure out what half of 0.180 is, and if we use the calculator, we'll get 0.0900 moles of O2. And now when we're in moles of a gas and we have STP, we can use the relationship that 1 mole of our gas at STP is going to occupy how much space? 22.4 liters. And what we have is 3 sig figs for 0.0900 and 3 sig figs for 22.4, and that gives us an answer of 2.02 liters of CO2. And that is the end of this section. In the next video, we'll do the ideal gas law. Okay, bye-bye.